Welcome to DAR Tutors for online and home tuition. In this video, we will explore chi-squared, or H2, hypothesis tests, which are a cornerstone of IB mathematics, applications and interpretation higher level. By the end of this session, you will be able to perform two critical tests. First, the goodness of fit test. This test helps us determine if an observed frequency distribution matches a theoretical distribution. In other words, how well does a proposed model fit the data we've collected? Second, the test for independence. This is used when we have two categorical variables. We want to know if there's an association or relationship between them, or if they are statistically independent. Both of these tests use a similar framework, which we'll break down into 6 clear steps. Understanding these two types of tests is essential for analyzing categorical data and making data-driven conclusions. We begin with the first type of chi-squared test, the goodness of fit test. Our objective here is to learn how to conduct this test from start to finish. This test is incredibly useful for validating statistical models. For instance, if you believe a set of data should follow a specific pattern, like the outcomes of a fair die, the goodness of fit test provides a formal way to check if your observation is consistent with that pattern. The core idea is to compare what we have observed, the frequencies, with what we would expect to see if our theoretical model were perfectly true. The larger the difference between observed and expected, the more likely our theoretical model is not a good fit. Let's work through the example of a person rolling a die. Suppose Rico rolls a die 60 times and gets these results. He rolls a 1 20 times, a 2 10 times, a 3 5 times, and so on. Rico's observed frequencies. The question is this die biased? This is where the goodness of fit test comes in. We want to see how well these frequencies fit the model of a fair die. Every hypothesis test begins with establishing the null and alternative hypotheses. This is the first and most critical step, as it clearly defines what we are testing. For our die rolling scenario, we are testing if the die is fair. A fair die has an equal probability for each outcome. So the null hypothesis, H0, is that the probability of rolling a 1 p sub 1 is 1 over 6. The probability of rolling a 2 p sub 2 is 1 over 6, and so on for all 6 faces of the die. This is our starting assumption, that the model is correct. We will look for evidence to challenge this assumption. The alternative hypothesis, H1, states that the null hypothesis is not true. In this case, it means the die is biased. More formally, H1 states that at least one of the probabilities, p sub I, is not equal to 1 over 6. If our test provides strong evidence against H0, we will reject it in favor of H1. Now that we have our hypotheses, our next objective is to calculate the test statistic for our data. This test statistic, denoted as chi-squared calc, quantifies the difference between our observed frequencies, FOBs, and the frequencies we would expect to see if the null hypothesis were true, FXPE. Let's calculate this step by step for Rico's die. First, we need to find the expected frequencies, FEXP. If the die is fair, each of the 60 rolls should be distributed evenly among the 6 outcomes. So the expected frequency for each number is 60 times 1 6, which equals 10. This is what we expect to see for each category if the die were fair. Now we can calculate the test statistic using our table of observed and expected frequencies. We calculate the term FOBS minus FXP squared divided by FXP for each outcome and then sum them up. After summing all the contributions from each category, we find that our calculated chi-squared statistic is 13.8. A large value here means a large difference between what we observed and what we expected. It's important to note that for exams, you are generally not required to calculate chi-squared calc by hand. You'll use your graphics calculator, which we'll demonstrate shortly. We now have our test statistic, but what does 13.8 tell us? To make a decision about our hypotheses, we need to compare this value to a benchmark. The next step is to find the degrees of freedom and the p-value. Degrees of freedom, or DF, for a goodness of fit test is calculated as the number of categories minus 1. This is because once you've determined the frequencies for k-1 categories, the frequency for the last category is fixed, since the total sum must be constant. In our example, we have 6 categories, the numbers 1 through 6, So the degrees of freedom is 6 minus 1, which equals 5. This value is crucial because it helps us understand the shape of the chi-squared distribution. Now let's talk about the p-value. In a goodness of fit test, the p-value is the probability of observing a chi-squared value that is as large as or larger than our calculated chi-squared calc, assuming the null hypothesis is true. Visually, the chi-squared distribution is always skewed to the right. The p-value corresponds to the area under the curve in the right-hand tail, starting from our H2 calc of 13.8. To find this, we use technology. Using a graphics calculator, we enter the observed frequencies into one list and the expected frequencies into another. We then perform a chi-squared GOF test, specifying 5 degrees of freedom. The calculator gives us a p-value of approximately 0.169. So we found that the probability of getting a result like Rico's, or one even more extreme, from a fair die is about 1.69%. We've reached the final step of our hypothesis test, making a decision. Our objective is to learn the rule for accepting or rejecting the null hypothesis and to interpret the conclusion in a meaningful way. To decide, we need a significance level, denoted A. If not specified, we usually assume a 5% significance level, meaning A equals 0.05. This level represents the threshold at which we are willing to reject the null hypothesis. The decision rule is straightforward. If our p-value is less than the significance level A, we reject the null hypothesis. This implies that our observation is highly unlikely if the null hypothesis were true. Conversely, if the p-value is greater than or equal to A, we do not have enough evidence to reject H0. We accept it and conclude that our observed data is consistent with the model. In our die rolling example, our p-value is 0.0169, which is less than our significance level of 0.05. Therefore, we reject the null hypothesis. This brings us to the final and most important step, interpreting our result in the context of the problem. We must clearly state what our statistical decision means in real-world terms. Since we rejected H0 in favor of H1, we conclude that there is sufficient statistical evidence at a 5 significance level to suggest that Rico's die is biased. The observed frequencies are too different from what we would expect from a fair die. The chi-squared goodness of fit test is a powerful tool, but it comes with an important limitation. Our objective here is to understand the conditions under which the test is reliable. The primary limitation is that the test is most reliable when the sample size n is large. The general guideline for the IB curriculum is that the test is appropriate if all expected frequencies are greater than or equal to 5. The term expected is key here. We must check the values in our FXP column. What happens if an expected frequency is less than 5? The test may produce an inaccurate p-value. In these cases, we must combine categories. Let's look at this example table, which has several small expected frequencies. Notice the categories for ages 40 to 50 and 50 plus. Their expected frequencies are 0.9 and 0.2 respectively. Since both are less than 5, we combine them with the preceding category, 30 to 40. The new combined category is 30 and over, and its expected frequency is the sum of the 3 original expected frequencies, which is 5.5. Now all our expected frequencies are 5 or greater, so we can proceed with the test. Combining categories also affects the degrees of freedom. In the original table, there were 6 categories, so DF was 5. After combining, we now have 4 categories, so the new DF is 4 minus 1, which equals 3. Always recalculate DF after combining categories. Now let's tackle a more advanced scenario. Sometimes, the parameters of the distribution we want to test are not given. We must estimate them from the data itself. This is our objective for this section. For example, let's revisit the data about the number of children born to 150 women. We want to test if this data comes from a binomial distribution, BNP, where n is 5, but we don't know the probability of success, P. In this case, our null hypothesis, H0, is simply that the data is from a binomial distribution with n to 5. To find our expected frequencies, we must first estimate the value of P. We do this by using the sample mean. We can calculate the mean number of children per woman, which turns out to be 2.6733. We know that for a binomial distribution, the expected value, or mean, is NP. So we can set our sample mean equal to NP to estimate P. We divide the mean by n till 5, which gives us an estimated p-value of 0.5347. We can now proceed with the test, calculating expected frequencies using B5 0.5347. However, there's a crucial adjustment. Because we estimated one parameter p, we lose a degree of freedom. The general formula for DF is the number of categories minus the number of estimated parameters minus 1. This is a very important rule for HL students to remember. In our case, with 6 categories and 1 estimated parameter, our degrees of freedom is 4. This brings us to a call to action. We hope you are finding this tutorial helpful. If you require expert personalized tuition for IB Mathematics, A-Level, or IGCSE, please do not hesitate to contact DAR tutors. Our experienced tutors can provide the guidance you need to master these complex topics and achieve your academic goals. Let's apply what we've learned to another important type of H2 test. Our objective is to learn how to conduct a chi-squared test for independence. This test is used when we have a sample of data classified into a contingency table based on 2 different categorical variables. Consider this example. We have surveyed 400 adults and classified them by their gender and whether they exercise regularly. This 2x2 table summarizes our observations. The question we want to answer is, are these 2 variables, gender and regular exercise, related to each other? That is, are they dependent or are they independent? As with any hypothesis test, we start by setting up our null and alternative hypotheses. The hypotheses for a test of independence are always formulated in a specific way. The null hypothesis, H0, states that the variables are independent. In this case, it means a person's gender has no effect on whether or not they exercise regularly. The alternative hypothesis, H1, states the opposite. The variables are not independent, or they are dependent. This means there is an association or link between gender and exercise habits. Once we have our hypotheses, the procedure for the test of independence is very similar to the goodness of fit test. Our objective is to learn how to calculate the test statistic and degrees of freedom for a contingency table. The chi-squared calculated value, chi-squared calc, uses the exact same formula. The sum of the squared difference between observed and expected frequencies divided by the expected frequencies. The difference is how we find the expected frequencies in a contingency table. Let's assume for a moment that the variables are independent, which is our H0. If they are independent, the probability of being male and exercising regularly is the probability of being male, multiplied by the probability of exercising regularly. From our table, the row total for males is 216 and the column total for exercise is 208, out of a total of 400 people. The expected number of males who exercise regularly is the total number of people, 400, multiplied by this probability, which simplifies to the row total times the column total, divided by the grand total. This gives us an expected frequency of 112.32 for that cell. We repeat this calculation for all 4 cells to create a complete table of expected frequencies. Next, let's find the degrees of freedom. For a contingency table with R rows and C columns, the formula is R1 times C1. This formula comes from considering how many cells we can fill freely before the rest are determined by the row and column totals. In our 2x2 table, we have 2 rows and 2 columns, so DF is 1 times 1, which equals 1. With the observed and expected frequencies and our degrees of freedom, we can use a calculator's chi-squared test function to find our test statistic and p-value. For this data, the calculator gives us chi-squared calc approximately 0.2117 and a p-value of about 0.641. Just like the goodness of fit test, the test for independence has an important limitation. Our objective is to understand Yates's continuity correction and when to apply it. The problem arises when the degrees of freedom is 1, which always happens in a 2-by-2 contingency table. The chi-squared distribution is continuous, but our observed data is discrete. Yates's correction helps bridge this gap, especially when the sample size is small. The rule of thumb for when to use the correction is often tied to the expected frequencies. If any expected frequency is less than 10, or sometimes less than 5, it's recommended. The IB curriculum states to apply it when DF equals 1. The formula looks complicated, but it's a small adjustment. For each term in the sum, we find the absolute difference between the observed and expected frequency, subtract 0.5, and then square it. The effect is to slightly reduce the value of the H2Calc statistic, which makes it harder to reject the null hypothesis. It's important to know that when you use Yates's correction, you cannot use the built-in H2 test function on your graphics calculator. You must calculate H2Calc by hand. Let's revisit our gender and exercise example. The calculator gave us H2Calc 0.217. Let's recalculate with Yates's correction, using the expected frequencies we found previously. We calculate the term, minus fxpop minus 0.5 for each cell. For example, for males who exercise, FOBS was 110 and FXP was 112.32. The absolute difference is 2.32, and subtracting 0.5 gives 1.82. We square this and divide by 112.32 to get 0.0296. Summing the contributions from all cells gives us a new H2Calc of approximately 0.139. As expected, this is smaller than our original value of 0.217. This correction is essential for 2-by-2 tables to ensure a statistically sound conclusion. So far, we've used the p-value method. Another common approach to hypothesis testing is the critical value method. Our objective is to learn this alternative method. The critical region is the set of all possible test statistic values that would lead us to reject the null hypothesis. It's the zone of rejection. The critical value, H2 crit, is the boundary of this critical region. If our calculated test statistic falls into the critical region, meaning H2 calc is greater than or equal to H2 crit, we reject H0. How do we find this critical value? We use a table of critical values. This table is organized by degrees of freedom and significance level. Let's use the table from your notes. In our first example, we tested Rico's dye at a 5% significance level, A equals 0.05, with 5 degrees of freedom, diffiogs phi. We find the row for 5 degrees of freedom and the column for a 0.05 significance level. The value at their intersection is 11.07. This is our critical value. So we reject the null hypothesis if our calculated H2 value is 11.07 or greater. Our H2 calc was 13.8, which is greater than 11.07. Therefore, we reject H0. We get the same conclusion as with the p-value method, which we would expect. Let's summarize. You can choose to use either the p-value method or the critical value method. The p-value method asks, how likely is my result, and compares that likelihood to A. The critical value method asks, is my result extreme enough to reject H0, and compares the test statistic to the critical value. Let's put everything together with an IB-style practice question. Our objective is to apply the full 6-step hypothesis testing process to a new problem. Here is the problem. A factory claims to manufacture glass, agate, alabaster, and onyx marbles in a specific ratio. Aggie counted the marbles and found 19 glass, 16 agate, 13 alabaster, and 2 onyx. We need to conduct a H2 goodness of fit test at a 5% significance level to determine if the manufacturer's claim is justified. The first step is to state our hypotheses. The null hypothesis is that the distribution of marble types follows the claimed 4:2:1 ratio. The alternative hypothesis is that at least one of the proportions is incorrect. Step 2 is to state the significance level. The problem specifies a 5% significance level, so A equals 0.05. Next, we calculate the expected frequencies, FXP. The total of the ratio is 4 plus 2 plus 2 plus 1, which is 9. We divide the total number of marbles, 50, according to these proportions. Let's continue with our solution. We have our observed and expected frequencies. Before calculating anything further, we must check the limitations. Our expected frequencies are approximately 22.22, 11.11, 11.11, and 5.5. All of these values are 5 or greater. This means we do not need to combine any categories, and the chi-squared test will be reliable. Now let's find our test statistic. We'll use a graphics calculator for this. First, enter the observed frequencies into a list, say L1, and the expected frequencies into another list, L2. L1 contains the counts Aggie found, and L2 contains the values we just calculated. Next, we calculate the degrees of freedom. There are 4 categories, so the degrees of freedom is 4 minus 1, which equals 3. Now go to the Stat Tests menu and select the chi-squared goodness of fit test. Set the observed list to L1, expected to L2, and degrees of freedom to 3. Then select Calculate. The calculator output shows a chi-squared calculated value of approximately 8.358 and a p-value of about 0.0392. Now for the final 2 steps of our first practice question. We need to make a decision and write our conclusion. We compare our p-value of 0.0392 to the significance level alpha of 0.05. Since 0.0392 is less than 0.0, we reject the null hypothesis. Alternatively, we can use the critical value method. For 3 degrees of freedom and a 5% significance level, the critical value chi-squared crit from the table is 7.81. Our calculated chi-squared calc of 8.358 is greater than the critical value of 7.81, so we again reject the null hypothesis. Finally, we interpret our decision. We conclude that there is sufficient evidence to reject the manufacturer's claim. Aggie's bag of marbles does not fit the ratio they claimed. Let's work through a second practice problem. This one uses the critical value method. Here are her results. 12 red, 17 yellow, 20 green, and 16 blue for a total of 65 lollies. The manufacturer claims they make equal quantities of each color. We need to test this claim at a 10% level of significance using the critical value method. Step 1. Hypotheses. The null hypothesis is that the colors are equally distributed. The alternative is that they are not. Step 2. Significance level. It's given as 0.1 sin. Step 3. Expected frequencies. If there are 4 colors and 65 lollies, and the distribution is equal, the expected frequency for each color is 65 divided by 4. This gives us 16.25 for each color. All are greater than 5, so the test is reliable. Step 4. Degrees of freedom. With 4 categories, the degrees of freedom is 4 minus 1, which equals 3. Now we can find our critical value from the table. For DFR3 and AFROPI.10, the critical value H2 crit is 6.25. Step 5. Test statistic. We must calculate this by hand since we need to compare it to the critical value. Let's organize our work in a table. For red, 12 minus 16.25. Squared divided by 16.25 is about 1.10. We do this for all colors and sum them up to get a H2 calc of approximately 1.785. Step 6. Decision. We compare our calculated statistic 1.785 to the critical value 6.25. Since our H2 calc is smaller than the critical value, it does not fall into the critical region. We therefore accept H0. Step 7. Conclusion. At a 10% level of significance, there is no evidence to reject the manufacturer's claim. The observed distribution of colors is consistent with the claim of equal quantities. Here is our third practice question. This time, we'll work with a test for independence on a 3x2 contingency table. They surveyed customers and found these initial satisfaction levels. After making changes to their internet plans, they surveyed a different, larger sample of 233 people and got these results. The question is, were the ISP's changes effective? We will conduct a goodness of fit test to compare this new distribution to the original one. Step 1. Hypotheses. The null hypothesis is that the changes had no effect, meaning the proportion of customers in each category is still the same as the initial proportions. The alternative is that the distribution has changed. Step 2. Significance level. The problem asks for a 1% level, so A equals 0.01. Step 3. Expected frequencies. First, we need the initial proportions. Based on the first survey, these were the proportions. Now we find the expected frequencies in the new sample of 233 people, assuming these proportions hold. For very satisfied, we expect 5% of 233, which is 11.65. All of these expected frequencies are greater than 5, so the test is valid. Let's complete our third practice question. We have our hypotheses, significance level, observed and expected frequencies. We can now find the test statistic and conclusion. Step 4. Find H2 calc and DF. There are 5 categories in our table, so the degrees of freedom is 5 minus 1, which equals 4. We'll use our calculator. Enter the observed frequencies in L1 and the calculated expected frequencies in L2. Perform the H2GOF test with DF equals 4. The calculator gives us a H2 value of 14.34 and a very small p-value of approximately 0.0643. Step 5. Decision. We compare our p-value to our significance level of 0.01. Since 0.0643 is less than 0.01, we reject the null hypothesis. Alternatively, let's look at the critical value. For DF4 and A0.01, the critical value from the table is 13.28. Our H2 calc of 14.34 is greater than 13.28, so we reject H0. Step 6. Conclusion. We conclude that at the % significance level, there is sufficient evidence that the distribution of customer satisfaction has changed since the ISP made adjustments to its plans. In the next part of this problem, you would analyze the contributions to the chi-squared statistic to see exactly where the biggest changes occurred. Our fourth practice question involves a 2x2 contingency table. This is important because it will require the use of Yates's continuity correction. The table shows his guesses against the actual result. For example, he guessed heads 54 times, and it actually was heads. We need to test at a 5% level of significance whether Horace's guess and the coin toss result are independent. This is a test for independence. Step 1. Hypotheses. H0. The guess and the result are independent. H1. They are dependent. Step 2. Significance level. A equals 0.05. Step 3. Degrees of freedom. It's a 2x2 table, so DF is 1. Since DF equal to 1, we must use Yates's continuity correction. Let's find the critical value now. For DF01 and A005, the critical value from our table is 3.84. Step 4. Expected frequencies. For each cell, we multiply its row total by its column total and divide by the grand total. For guess heads, result heads, the expected frequency is 104 times 95, divided by 200, which is 49.4. Let's check the limitation. Our expected frequencies are 49.4, 54.6, 45.6, and 50.4. All are greater than 5, and in this case, all are also greater than 10, so the test is perfectly valid after the Yates's correction. We're in the final stretch of our fourth practice problem. We have calculated the expected frequencies and identified that we need to use Yates's correction. Step 5. Calculate the test statistic using Yates's continuity correction. Remember, we must do this by hand. We'll work with the absolute differences. FOBS minus FEXP. Let's list the values. Notice the absolute difference for each cell is 4.6. This is because the cells are constrained by the row and column sums. Now we apply the correction. For each cell, we take this absolute difference, subtract 0.5, square the result, and divide by the expected frequency. Summing these gives us our calculated chi-squared value of approximately 1.351. Step 6. Decision. We compare H2 calc to our critical value from before. H2 crit equals 3.84. Since 1.351 is less than 3.84, we do not reject H0. Step 7. Conclusion. We conclude that there is not enough evidence to say that Horace's guess and the coin toss result are dependent. In other words, there is no evidence that Horace can predict coin tosses. His accuracy is consistent with random chance. For our final practice question, we'll work with a 3x3 table. Our objective is to apply the test of independence to a larger dataset. An investigation considers the relationship between a person's level of education and their level of business success. The results are summarized in this contingency table. The problem states that for this test, there are 9 degrees of freedom and a 1% significance level. The critical value H2 crit is 21.67. We need to test if there is a link between education level and business success. Step 1. Hypotheses. H0. The variables are independent. H1. They are dependent. Step 2. Significance level A equals 0.01. Step 3. Degrees of freedom. The table has 4 rows and 4 columns. So DF is 41 times 41, which is 9. The critical value for DF for 9 and A is DRPA1 is 21.67 as given in the problem. We need to perform the test. For such a large table, manually calculating the A2 calc is very tedious. This is a perfect example of when to use the Ch2 test function on your graphics calculator. First, we must enter the entire observed contingency table as a matrix into our calculator. Go to the Matrix menu, select Edit, and choose a matrix, say A. Set its dimensions to 4 rows by 4 columns and carefully input all 16 frequencies from the table. Once the matrix is entered, go to the Stat Tests menu and select H2 test. Set Observed to the matrix you just created, e.g. A. The calculator will automatically calculate the expected frequencies and store them in a second matrix. But the calculator output shows a calculated chi-squared statistic of approximately 36.43 and a p-value that is virtually 0. Now let's make our decision and conclude our final practice problem. Step 6. Decision. We compare our calculated $2 value of 36.43 with the critical value of 21.67. Since 36.43 is greater than 21.67, it falls into the critical region, and we must reject the null hypothesis. Alternatively, we can use the p-value. The p-value was effectively 0. This is much smaller than our significance level delta TETU issues 0.01, confirming our decision to reject H0. Step 7. Conclusion. We conclude that at a worst-sense significance level, there is strong evidence that education level and business success are not independent. There is a statistically significant link between the two variables. To learn more about this link, we would examine the calculator's CNTRB list, which shows the contribution of each cell to the total $2 statistic. This would tell us which specific education and success level combinations are most different from what we would expect under independence. Let's summarize the key takeaways from our comprehensive look at chi-squared tests. We learned about 2 main types of chi-2 tests: the goodness of fit test and the test for independence. The goodness of fit test compares observed data to a theoretical distribution. We use it to see if a model like a fair die or a specific ratio is a good fit. The degrees of freedom is the number of categories -1 or -1 for every parameter estimated. The test for independence is for contingency tables, helping us decide if 2 variables are related or not. Its degrees of freedom is the number of rows -1 times the number of columns -1. The overall procedure is the same for both tests, involving calculating observed and expected frequencies, a test statistic, and a decision based on p-values or critical values. Finally, we emphasize 2 crucial limitations. All expected frequencies must be 5 or greater, and for 2x2 tables, where DF1, Yates's continuity correction should be applied manually. Mastering these concepts and procedures is essential for success in your IB Mathematics HL exams. If you need more personalized help, contact DAR Tutors for expert tuition. Thank you for watching this DAR Tutors video on H2 hypothesis tests. We encourage you to review the concepts and work through the examples again to solidify your understanding. Remember, practice is key to mastering these topics. For more in-depth explanations, additional practice, or personalized support, contact us through our website. We are dedicated to helping IB, A-Level, and IGCSE students achieve their full potential. We wish you the best in your studies. Goodbye.